Hello, welcome back. I now want to talk to you about something that's called a loop transformation. And loop transformations can be used to turn arbitrary problems involving the feedback of a linear component and a sector-bounded nonlinearity into precisely the special case of the interconnection of a positive real or strictly positive real transfer function with a sector-bounded nonlinearity lying in those two quadrants, which we could then analyze with the passivity theorem. So what we're really showing today is that the passivity theorem, in fact, proves the circle criterion that we saw before, and the missing link between these two cases are loop transforms, and that's what I want to tell you about, really. So we start off with precisely the feedback setup that we had at the beginning, and I'm going to put in a few bits and pieces onto this picture. You want to just ignore them for now, but we need them there. So we're interested in analyzing the feedback interconnection of a linear system G with output Y in feedback with a sector-bounded nonlinearity. And before we looked at negative feedback conventions, I'm now just going to dump the negative feedback as a minus sign inside this H. And so we have our H is sector-bounded with slopes K1 and K2. And for us, K1 is going to be bigger than or equal to K2. And now I want to do a sequence of modifications to this picture which will not alter stability, but will allow us to regroup various blocks so that we end up with a new system where this H becomes there's a corresponding H that lies in these quadrants, and then we'll show that meeting the, we won't show, but we'll discuss why meeting the circle criterion is then equivalent to this transfer function being strictly positive real. So loop transformations are alterations to this block diagram that don't affect stability. And the first loop transform I want to make is the following. That should be no, I want the circle there. So we're going to take a negative feedback with our parameter K2. And now we're going to do a corresponding transformation that is a feed forward that is going to completely cancel this out. So why has this transformation not affected stability? Well, let's just look at this signal here. So before we put in these K2s, this signal was just equal to the output of our nonlinearity. So if I call that signal U, this signal here was just equal to U. You can imagine there's ones in these blocks. But what is it equal to now? Well, it's equal to this minus K2 times Y. So this, let's call this, I don't know, I'm going to want to call it U tilde. So this signal here is U tilde minus K2Y. But what is U tilde currently? U tilde is U plus K2Y. So you see the effect of this, of pushing this K2Y through, is cancelled out by putting a negative feedback of minus K2Y in here. So this signal is still completely the same, and so its stability has not been altered by performing this loop transformation. What are some other loop transformations we can do that won't affect stability? Well, something that we could do is we could divide by 1 over K1 minus K2, as long as we multiply by K1 minus K2 here. So the product of these two blocks is just 1. So whatever flows in here is equal to whatever flows out here, no matter what's in these blocks. So if these were 1s, or if they're K1 minus K2 and 1 over K1 minus K2, the map from here to here is still the same. So this is another stability-preserving loop transformation. And the final one that we need is we want to put a long feed forward in here, no blocks this time, so with a plus, and we're going to then put in the corresponding feed back. like this. And this is also stability preserving, so nothing changes here for exactly the same reason nothing changed when we put in this negative feedback and positive feed-forward pair. So these are a bunch of transformations that we can do that don't affect stability of this setup, but we're now going to just group things together to rewrite this as a new feedback interconnection. And it's this new feedback interconnection that we're going to be able to analyze with the passivity theorem. So what we're going to do is we're going to sort of lump everything here into a new nonlinearity and lump everything up here into a new linear system. So this is the same as the feedback of G tilde, which is our new linear system, in negative feedback with a new nonlinearity, H tilde, and to make all of the signals match, this can be Y tilde. This is the nonlinear bit, but I need this minus sign. So this signal here is actually minus U tilde. So G tilde is everything here lumped together into a single transfer function, and H tilde is everything here lumped together into a single nonlinearity. So what happens if we do this? Well, let's just talk a little bit about what minus H tilde becomes. And to do this, we're just going to imagine actually, so our nonlinearity lies in this sector here. Just to keep our calculations simple, we'll just assume this nonlinearity is linear. It'll just make the manipulations a bit easier. You can go away and check for yourself that this all works, even if we look after a nonlinearity correctly as well. So what is the effect of all of these steps? So let's say that whatever is minus h dot, we don't know what it is, but it's some function k, and then let's just give this variable a name. So this is the line kq here. So this is our function h. So what is minus h? Well, minus h is just, we just flip things. So now we have minus something with a slope of minus k. So this, the nonlinearity from here to here is just some straight line function we're assuming for now, which has got slope minus k. What happens now if we put this plus k2 in? So we move to this setup, and what's the effect of adding a feed forward with plus k2? Well, this just has the effect of pushing all the slopes up by k2. So now we've got something that lies between something with a slope of 0 and a slope of minus k1 plus k2. And then on nonlinearity, this has got slope minus k plus k2. What happens next? Well, now we just look a little bit wider, so now we get pulled through here. And so if we look at the nonlinearity from here to here, well, it's just the whole thing, but with its size divided by k1 minus k2. Now k1 is bigger than k2, so this is just rescaling the slopes. So what do I get? I get something. Now this has got slope minus 1. And this thing here has got slope minus k1 plus k2 all over k1 minus k2. Okay, we're almost there. Let's call this k bar. So we don't know what k bar is, but we know that k bar lies in the range of, it's somewhere, it's some value between minus 1 and 0. So to complete things, and this is where we're going to use the linearity to our advantage, what happens when we start to include this feedback term here? Well, if it's just linear, we can just use our feedback formula. So then the nonlinearity from here to here is simply given by k bar over 1 plus k bar. So we've got that in the nonlinearity, we've got a negative feedback, so we get k bar over 1 plus k bar. So let's try to understand what this looks like. So let's just graph this as a function of k bar. And what do we get? Well, if we graph this as a function of k bar, well, if we put k bar is equal to -1, we get some asymptote. If k bar is equal to 0, our function is equal to 0. As k bar goes to infinity, we go to 1 here. So that's our height 1. So now we see that if we were to graph our function, it looks like this. And so what does this show us? Well, if this is k tilde, so this is the nonlinearity from y tilde to u tilde, well, if k bar lies between -1 and 0, then k tilde lies between 0 and -infinity. And now we put in our minus sign, and we see that minus k tilde lies between 0 and infinity. So putting all of this together shows that h tilde now is sector bounded with slope between 0 and infinity. So whatever h tilde is, it lies over here. And so this has successfully actually transformed our general sector-bounded nonlinearity into precisely the sector-bounded nonlinearity that we can analyze with the passivity theorem. So what's the final piece of the puzzle? Well, we just need to work out what this transfer function g tilde is. And so we can just do our transfer function manipulations. So what's this transfer function here? This is just, so g tilde is equal to, well, it's equal to k1 minus k2 multiplied by this transfer function here plus 1. So this transfer function, this is just g over 1 plus k2g. And then we've got plus 1 here. And so we just need to do some manipulations there. And if we simplify this, we get 1 plus k1g over 1 plus k2g. So what we've managed to show is that our original feedback interconnection, so G in feedback with a sector-bounded nonlinearity, we managed to show that this is stable as long as this transfer function here is positive real or strictly positive real, because this has transformed our sector to lie in these quadrants, and so by the passivity theorem, we need this transfer function to be positive real or strictly positive real, and if it is, then we can apply the passivity theorem. So the final piece of the puzzle is actually trying to understand how the positive real condition connects to the circle criterion characterization connects to the positive real characterization. And this is actually done through Mobius transform. So this thing here, this is an example of Mobius transform. And we have two pictures of the right half plane. And we have a picture with 1 over k1 and minus 1 over k2. And we have the function z tilde is equal to 1 plus k1 z over 1 plus k2 z. So here we have the z tilde plane, and here we have the z plane. And what you find is that, well, Mobius transforms are a special class of function, and they map circles into circles or half planes always. And so we've got two pictures of the complex plane. And what we have is, so the result that we need is that the Mobius transform of this form, well, this circle that's cuts through the negative real axis at -1/k1 and -1/k2 and is symmetric, is mapped by this transformation into the left half plane here. And so what that means is the statement that a Nyquist diagram lies in this open region over here is equivalent to a Nyquist diagram lying over here. So in other words, strictly positive realness of this transfer function here is equivalent to the Nyquist diagram lying in this region over here. And there's actually an additional subtlety. You're actually guaranteed to preserve encirclements in exactly the way that you would need. So the condition that we have the right number of encirclements to satisfy the Nyquist criterion corresponds to the poles, to the systems being asymptotically stable or marginally stable. So in the strictly positive real world, the transfer function lying in this half plane corresponds to the transfer function lying anywhere outside of this circle. And the condition poles, the transfer function is asymptotically stable or marginally stable, translates into the encirclements of this region satisfying the Nyquist criterion. And so we have a direct correspondence between all these things. So the point of all of this is that there are these nice loop transformations that you can apply to systems, to feedback systems that will not alter stability. And by applying these loop transformations in a clever way, we can turn our original problem involving the feedback of a linear transfer function with a general sector-bounded nonlinearity into the special case that corresponded to the interconnection of something that's positive real or strictly positive real with a nonlinearity lying in these two quadrants. And then through the KYP lemma, we're able to prove stability of this case using the Lyapunov argument that we saw before. So what we see here is a kind of a long connection between the circle criterion that we saw at the beginning and the Lyapunov stuff from the last lecture.